A certain HMO has an important decision to make. To create a more efficient and profitable business, the HMO will only allow doctors to prescribe one drug for a particular purpose, even though there may be other similar drugs on the market. Two competing pharmaceutical companies have drugs that are designed to reduce cholesterol levels. Both drugs have been on the market for several years and are effective for most people. Your job is to help the HMO determine which drug they should use based on its effectiveness in the general population. To make sure the study is not biased, it will be double-blind. Thus, neither the subjects nor you will know the identity of the drugs, which have been prepared by an independent lab and labeled Drug A and Drug B. To obtain subjects for your study, a list of clinics in the U.S. was obtained and one clinic was randomly selected. Within the clinic, nearly 50 people volunteered to be in the study. Of the volunteers, 24 were selected to participate based on their gender, age, frequency of exercise, 0 equals low, 2 equals high, and their initial cholesterol count. These 24 were selected so that there were an equal number of each gender, an equal number of each exercise level, and equal numbers of similar age and initial cholesterol count. Your job is to assign them to treatments and determine which drug is more effective. To measure the success of each drug improvement, you will subtract their final cholesterol count from the initial cholesterol count, initial minus final. Thus, the higher the difference, the more effective the drug was in reducing the cholesterol of the subject. This has already been done for you in the tables that you have. So what we're actually going to do is not really run the experiment. We're going to, in our activity, the experiment has already been run. We're going to look at the effects of different blocking techniques in evaluating the results. So you have a table which is sorted by age, so lowest to highest age, and you have a table that is sorted by initial cholesterol level, lowest to highest. In both of the tables, anything that is to the right of the dotted line are values that would not be known until after the experiment was done. So when we're actually doing our random selection, we're going to fold that on the dotted line and only look at the gender, age, exercise level, and initial cholesterol. In our first example, we are going to randomly choose 12 different numbers from 1 to 24 using our random number generator on the calculator and assign those subjects to drug A. Obviously, they have to be 12 different people. And then the remaining 12 would be assigned to drug B. I have done this as an example. These are the 12 numbers I got for drug A, and these are the 12 I got for drug B. Then I'm going to go through then and the ones that were assigned to drug A, I'll use this as their improvement. If they were assigned to drug B, I would use this number as their improvement. So I recorded all the improvements. Notice the negative improvement is the cholesterol level actually went up by 1 point. And then I'm going to calculate the mean improvement for each drug. In my simulation, the average improvement was better for drug B. But in the other class members, we had some picked drug A being better and some picked drug B. We saw this range of results. These were the mean improvement levels for drug A, and these were the mean improvement levels for drug B. So although we saw that overall most of the trials had higher levels in general for B than for A, there were quite a few trials where a person got a higher level for A than for B, and so this came out as a rather inconclusive result. There's so much variability and so much overlap in the results, it's difficult to ascertain which drug actually is the better drug. So now we're going to try blocking by age. Perhaps age has an influence on how people react to drug A or drug B, and so we may maybe that will help reduce some of the excessive variability. So in this case, we went back to the table that was arranged by age, and we picked the two first people to be together as one block, the second two people to be together as one block, and so forth. So the two people with the most similar ages. Within each block then, so looking at person in row 1 and person in row 2, then I randomly selected, using a random number generator, I put in 1 or 2. And if the number 1 came up first, then the smaller number went to drug A, and if the number 2 came up, then the larger number went to drug A. So for example, with 6 and 7, if I got a 2, then I would assign 7 to drug A and 6 to drug B. If I got a 1, I would assign 6 to drug A and 7 to drug B. So I went through and did that. Here were my results. I ended up with a mean of 19.3 for drug A and 28 for drug B. So I had an even more, it looked even more promising for drug B, but still in the class as a whole, 2 people ended up with drug A having a better improvement than drug B. Even though we have a little bit of reduction in variability, we still had quite a bit of overlap and somewhat inconclusive results. Looking at the teacher materials for this, I feel like the variation actually is not typically reduced by this much. We just we had a small sample in our class, but the probably is not going to reduce the variability very much, and we'll see later on why A is not very effective as a blocking variable. If the ranges were about the same, we would say it's not effective at all. There is a slight decrease here, like we said, but I don't think in general that age is going to be a helpful variable to block on. Then we did the same thing with cholesterol. So we paired together the people that had the most similar cholesterol levels, and within each block of 2, we randomly assigned 1 to drug A and 1 to drug B. So 1 and 2, 3 and 4, 5 and 6, 7 and 8, and so forth. And notice I randomly assigned which one got which, so it's not always 1 and 2. Here I have 6 and 5. Here I have 9 and 10, but here I have 12 and 11, because I was randomly assigning which one got which drug. Calculating the mean improvement level, in this case, everyone in our class doing the same kind of simulation, we each had a different result in our table. We all got the result that drug B improved cholesterol levels more than drug A. You can see here a much more reduced variability. We still have about the same mean and standard deviation for both drug A and both drug B, but there is much less variation when blocked by age. So this means that initial cholesterol is an effective blocking variable, because we now have conclusive results. We now see very little overlap. Everybody in the group saw that B was better than A. Now, why does this work this way? Taking all of the 24 people and plotting their age against their improvement using drug A and their age against their improvement using drug B, we can see that there is almost no correlation at all between drug A and improvement using A or improvement doing B. Both of those would have a very low R value. There's almost no association at all. But when we look at initial cholesterol and improvement, we see a very strong linear pattern. So when we see a variable that is strongly associated with a response variable, that is a good variable to use as a blocking variable. Without blocking, it would be hard for the researcher to tell how much of the difference in improvement is because of the difference in medicines and how much is due to the differences in initial level of cholesterol. People with higher initial levels of cholesterol tended to report higher levels of improvement overall. So it's hard to tell how much of it's the drug and how much of it's the initial cholesterol level if we're just totally randomly assigning people. So that's why pairing up by cholesterol level helped reduce that amount, that variability, and so we could see the effect of the response, of the medicine more clearly. Now, if we look at the other last 2 variables that we have listed, gender and exercise level, which would be more helpful to block by? Well, you can see there is no linear association at all for gender. We don't see any positive or negative slope, pretty much undefined slope here, nothing at all that would indicate that gender has any relationship to cholesterol level improvement, whereas exercise level, we definitely see a strong trend that people who exercise more tended to see less improvement overall, perhaps because their cholesterol level was already as good as it was going to get. Maybe exercise already lowers cholesterol level. So blocking by exercise level appears to be a good idea. In a real experiment, though, we wouldn't do we wouldn't know the results in advance. So how would we decide which variable would be beneficial to use in blocking? There'd be a couple ways, either by prior knowledge about the relationship between variables, maybe from a previous experiment, or maybe doing a small pilot experiment first. Then that would make a good case for a blocking variable. So for our last trial, what we did was we blocked by exercise and initial cholesterol level. Now that was a little more complicated. So going back to our chart where we were sorted by cholesterol level, what we did was we looked at, first of all, exercise level exercise level 0. So looking at exercise level 0, I think this is the way I did it first. I picked the two lowest initial cholesterol levels associated with exercise level 0. So 15 and 18 were grouped together as a block. Then I would look at the next two lowest cholesterols for exercise level 0. So 19 and 20 were associated as a block. 20 and 21, 22 and 23, or 20 and 20, or 20, sorry, 19 and 20, 21 and 22, and 23 and 24. Then we went to exercise level 1, and I grouped together 5 and 10 because they were the two lowest cholesterol levels associated with exercise level 1, and then 11 and 12, and then 13 and 14, and then 16 and 17, and so forth, and the same thing with 0. So if we go to that last trial, we'll see then these were the ones that were paired together, 15, 18, 19, 20, 21, 22, etc., and then randomly selected which of the two was assigned to A or B, and then calculated all of the mean improvements again. Once again, very conclusive results. All 8 in our class got that B was better than A, and when you see the graphs, you see that the range of values was only 3.3 for drug A and only 1.5 for drug B. Basically everything clustered right around about 25.5. There was no overlap in the graphs at all. So we see that there is clear evidence now that drug B is the better drug. So blocking by exercise level and initial cholesterol, since they were both very strongly associated with the response variable of improvement in cholesterol level, they reduced the variation in the response variable due to these other factors and type of medicine. So these two both influenced the level of the response variable so much that removing them made it very clear which medicine was the most effective. So what is the overall purpose of blocking? It's to reduce variability from variables other than those in the treatments, so the effect on the response variable can be seen more clearly. The treatments here were which medicine they got. We wanted to see the difference in their cholesterol improvement based on medicine alone. So by blocking by cholesterol and exercise level, we eliminated those two variables from influencing the response variable. We eliminated because we only compared people with similar exercise levels and cholesterol levels, so anything we saw should have been due only to the medicine. We always block on whichever variable or variables are most strongly associated with the response variable, and we would not block if we have no reason to believe that a variable would have any effect on the response variable. In this case, we could have blocked by gender, but it would have been a useless thing to do because gender seemed to have really no effect on the improvement in their cholesterol levels.